Hello students, and welcome back to another lovely day of chemistry. I'm glad to have you all here. So today we're going to start talking about single replacement reactions. So in a single replacement reaction, it's a reaction that is going to occur between a solid metal and an aqueous ionic compound. I know you haven't seen that word aqueous before, or you probably did back in 9th grade, but maybe don't remember it. What an aqueous solution is, it is something that is dissolved in water. And I think a lot of times students wonder, well, why don't we just call that liquid? The reason that we don't call that liquid is in chemistry terms, when you say liquid, you are talking about a pure substance. That is something that is the same the whole way through. And as you can probably guess, the main pure substance that we would work with in this classroom is water. And that's when I give you like the distilled or the bottled water. Any other time we are talking about an aqueous solution. So think back to your ionic versus covalent lab when you had your test tube or your beaker and you would put like your copper chloride or something in there and then you'd add the water. Well, when you added that water to it and that copper chloride broke apart, you now had what we would call an aqueous, not a liquid solution. So aqueous just means something dissolved in water, or if you even look at the delicious tap water from our sinks, I'd call that aqueous because there's fluorine and calcium and a bunch of other stuff in there. So continuing on with a single replacement reaction. What's going to occur in a single replacement reaction is that the metal is going to replace the metal in the ionic compound, as you can see here. So metal 1 is going to replace metal 2. And a great example of this is if you picture when I had that sheet of aluminum foil, and I did this demo in class. So there's that sheet of aluminum foil, and then I took and I added that like bluish, greenish copper chloride, and I just dumped a pile of this copper chloride on there. And nothing happened, right? There was no reaction while they were both solid. And then what I did is I took and I added my water bottle onto that, and I actually poured some water on there. Well, if you think about this in terms of what you have done in class, copper chloride as a solid is going to sit in that crystal structure that we learned about. And so you're just going to end up with these coppers, these coppers and these chlorines just kind of stacked on top of each other and alternating. Because that's what ionic compounds look like as a solid. But then, if we took and we dump this into water, so if we take this copper chloride and we dump it into water, well, what that water allows us to do is it's no longer in that structure where everything's happy. You're going to have those coppers are going to break apart. And that's essentially what happened, or the copper chlorides are going to break apart into their ions. And that's basically what happened when I did that demo, and we were able to see the reaction start to occur once water was added, because it took this copper chloride and it actually broke it apart into ions like you would see here. And what that allows now is for that aluminum, those aluminum atoms to go in, and those aluminum atoms are going to actually start finding those chlorines. And so this reaction is able to occur. So essentially you can just think about it as copper. If this was your copper, this was your chlorine. I'm sorry, your copper and your aluminum. Copper is essentially going to get kicked out, and aluminum is going to come in and replace it. And so you'd end up with copper by itself, and aluminum is now going to be bonded to chlorine. But a common mistake that students make, and you know what, you'll actually see this on the next slide here. A common mistake students make when they see this is they would actually be really tempted to write this as AlCl2, because the thought process is, oh, well, you know, there's 2 chlorines bonded to copper, so aluminum's going to bond to 2 chlorines. aluminum does not care what copper does. Aluminum is aluminum, and it's going to do what it wants to do. Don't forget what you learned last unit. Aluminum has 3 valence electrons. So guess what? It's going to want to find 3 chlorines that it can give electrons to. And so that's exactly what aluminum is going to do. So that's why you need to be very, very careful, and please note, you need to solve for what's going to happen. You cannot just assume that, oh, because copper bonded to 2 chlorines, aluminum is going to. Nope. And hopefully, based on what we learned yesterday, you're now thinking to yourself, well, now we have an issue. These reactions right now are not balanced because we have 2 chlorines on the left and 3 chlorines on the right. So we would need to go through and actually balance this. And so to balance this, I'm going to, and if you're good with balancing, you understood that yesterday, you can fast forward. But otherwise, to balance this, I'm going to look at it. I have aluminums, I have coppers, and I have chlorines. 1 aluminum on the left, 1 copper on the left, 2 chlorines on the left. 1 aluminum on the right, 1 copper on the right, but I have 3 chlorines on the right. Well, I kind of look at an issue because I'm like, well, aluminum's good, copper's good. Oh, chlorine's my issue. You'll notice that on this side, chlorine is going to increase by 2 at a time. That is, if I have a 1 here, I have 2 chlorines. If I have a 2 here, I'm going to have 4 chlorines. If I have a 3 here, 6 chlorines, and so on. Same thing on this side. This is going to go from, over here is going to go from 3 to 6 to 9 to 12, and so on. So we're going to go back to the idea of the least common multiple. What's the smallest number that both 2 and 3 are going to fit into? Well, it's 6. So my goal is going to be to get 6 chlorine on each side. To do that, I'm going to put a 3 in front of here. That's going to get me that goal of 6 chlorine, but I need to update. That's also going to give me 3 coppers. And sometimes students get a little nervous. Well, it was balanced. Why would I unbalance it? Honestly, you can throw whatever number you want to right here in front of copper when you're done. It doesn't matter. Who cares if you have to change that number in front of copper because it doesn't affect anything else. It's really easy. So we'll continue on. We got 6 chlorine like we wanted on the left. To do that on the right, I'm going to put a 2 right here. That's going to give me my 2 times 3, so that gives me my 6 chlorine. But again, that also affected our aluminum. So I need to update my aluminum down here to 2. And you know what? Now it's pretty easy for us to balance. To get 2 aluminum on the left, I throw a 2 right here. To get my 3 copper on the right, I put a 3 in here. And hey, look at that. We have a nice balanced reaction. So what this is telling me is that I'm going to need 2 aluminum atoms for every 3 copper chloride. And that's going to end up producing 2 aluminum chlorides and 3 copper atoms. And again, when I did that reaction in class, if you remember it, there's that red that shows up. That red is copper being pulled out of this green powder, which seems kind of weird, but when copper is bonded to chlorine, it actually produces that greenish looking color. But as soon as that chlorine is pulled out of the copper, or as soon as that copper is pulled out of this compound over here, it actually forms that reddish color that you'll see. For single replacement reactions, again, if we were to take time to predict this, well, metal is going to replace metal. And I do like students to kind of understand why. I notice when I do this in class, students will oftentimes be like, well, sodium is going to bond to potassium. Well, you know, if you take a minute to think about it, that's not going to happen. Yes, it's true, it's not going to happen because it's a metal and a metal. It's also not going to happen because think about electrons. Sodium has 1 valence electron, potassium has 1 valence electron. They're both trying to get rid of electrons. They're not going to bond with each other. And keep those fundamental chemistry pieces in mind. So potassium and sodium are going to switch places, so therefore it's now going to be potassium bonded to chlorine and sodium by itself. So potassium chloride would become our aqueous solution. Sodium would become our solid. And then don't forget, you need to balance charges. So if I look at potassium is +1, chlorine is -1, well, you know what, in this case, kind of balanced itself out. So we're good, and we can move on to the next example. Oh, another thing students will often ask, doesn't matter which order you write these in, so does it matter if I write potassium chloride and then sodium, or can I write sodium and potassium chloride? Doesn't matter at all. Couldn't care any less which order you write them in. If we look at the next reaction, again, magnesium is going to replace aluminum. So we're going to now have magnesium bonded to fluorine and aluminum by itself. What I would like you to do now is pause the video, and I want you to figure out, what did I do wrong here? Why is this not a complete reaction? All right, now that you've had a chance to think about that, hopefully you said something along the lines of, it's not charged, or you didn't balance charges. The other mistake I'll see students make is students will actually go through and they'll be like, oh, it's because it's MgF3. Because they think, oh, well, there's 3 fluorines on aluminum, so magnesium is going to bond to 3 fluorines. Again, magnesium could not care any less what aluminum does. Magnesium is going to do what it wants to do. Magnesium has a +2 charge. Fluorine has a -1 charge. So therefore, it's going to take 2 fluorines and 1 magnesium. So the way that you would write this, sorry, my erasers apparently decided to not work anymore. So the way that you would write this is you would need MgF2 plus aluminum. And then, you guessed it, you need to go through and balance your charges. Magnesium, balance your atoms, I mean. And so to do this, well, I can kind of see that same pattern as what we saw before. I have 3 fluorine on the left, 2 fluorine on the right, so I'm going to go with that least common multiple. And to balance this, I'm going to need 2 in front of this to give me 6 fluorine, 3 here to give me 6 fluorine, 3 magnesium here to balance out now, and then 2 aluminum there. If you're still confused on balancing, please find time to come in and see me. I would absolutely love to help you out. With activity series, please keep in mind, single replacements do not always occur. I mean, a great example is picture an aluminum boat on the ocean, right? Your ocean is quite literally an aqueous solution. And because it's salt water, I mean, that's sodiums and chlorines dissolved in water, right? Well, imagine if every single replacement reaction occurred and you took and you brought your nice aluminum boat out onto the ocean. Well, it'd be pretty terrifying when your boat suddenly starts dissolving because of a single replacement reaction. So these reactions don't occur. Some elements are more reactive than others. So keep that in mind as you make your way into the metal activity series lab, that some reactions do not occur, and that's a good thing. So what I would like you to do now is please pause the video. I want you to switch over, make sure you download the metal activity series lab, and then I would also like you to watch the makeup video that's towards the bottom of the Canvas page that deals with actually goes through and shows you the lab itself. So that way you can do the lab without coming in. So you can switch over to that. Good luck, have fun, and then once you finish the lab, come back to this video and watch the last couple minutes as I explain the next slide. So as you saw in the lab video, some reactions don't occur, some reactions do occur. And if you look at the back of your periodic table, you'll notice, or on the right side of your desk, you will notice this thing on there called an activity series. So what this activity series deals with is the elements near the top are what we have found experimentally to be the most reactive. Elements near the bottom are the least reactive. And hopefully you kind of notice this in your lab. For example, you may have had magnesium. Well, magnesium, when you had that as a metal, and then let's say you mix that magnesium with, in the lab you probably saw it mixed with like a copper nitrate solution. Well, this reaction absolutely occurred. You're going to have this reaction go through and it's going to produce magnesium nitrate and copper by itself. That reaction would occur. However, what you probably did not see is when you had, say, copper by itself, and you mix that copper with, I don't know, let's say aluminum nitrate. This reaction did not occur because copper is far more stable than aluminum. We can trust copper to be by itself. So the analogy that I always give students, think of lithium as being like that crazy guy in the fight. He's the guy that's like up in your face, yelling at you, telling you he's going to smash your face in, whatever. That's lithium. He's insane. Then you have copper, who's that person that's in the fight, and they're kind of like, whoa, man, you just need to calm down. It's okay. Like, don't worry about it. Right? Who are you going to help in the fight? Or who are you going to hold back? Not help. I hope you don't help anyone in the fight. Who are you going to hold back? You're probably going to hold back the crazy one, the person that's going insane, and you're going to trust the other person to kind of, let's not worry about that. It's that same idea here. Think of this nitrate, in this case, as being the referee. They're going to hold back the crazier person. So if we look at these examples on the left, and we compare potassium chloride and lithium. And chlorine in this case is the referee. So we have to figure out who are they going to hold back? Who's the crazier one? We see potassium is second on the list, and we see lithium. Lithium's going insane. Lithium is higher on the list. So guess what? Lithium needs to be held back. So we're going to end up with lithium bonded to chlorine because chlorine needs to hold lithium back, it needs to calm down. And we're going to trust potassium in this case to kind of do your own thing. And this would be aqueous and solid. If we look at the next example, we have barium versus calcium, and sulfate is going to be our referee. So if we compare barium right here to calcium, we see barium's crazier. So you know what? Sulfate needs to hold back barium. We can trust calcium a little bit more on their own. So guess what? We can just simply write no reaction is going to occur. Why? Well, sulfate is already holding back the crazier one, already holding back barium. If we look at the next one, we have iron versus lead. We find iron on our list is right here. We find that lead is down here. So you know what? Iron's going to be crazier, so iron needs to be held back. So again, this one would be no reaction is going to occur. If you have any questions regarding single replacement reactions, whether it's on your homework or in the lab, please make sure to find time to come in and see me.